Thank you so much for watching the Henry AI Labs YouTube channel. Recently, I've been really excited to work with Weaviate and Semi Technologies to learn about their vector search engine. Vector search engines are really cool for navigating through these data sets using these deep learning representations. Say we have things like contrastive learning where we're trying to learn these vector representations of images such that positive pairs are similar to each other compared to negative pairs. And we can do this with things like searching for nearest neighbors in these databases. You can use an image and then find the nearest image in the database by using the vector representation. Similarly, you can do this with text embeddings, and you can do things like querying this new generation of search engines using deep learning. But then also there's the symbolic side. And if you've seen things like criticism of deep learning with symbolic queries, you know that a neural network can't really do things like get me all the articles in this database that have a word count of less than 400 or any of these kind of symbolic aggregations. So this Weaviate technology of combining these vector representation search based on deep learning with these symbolic aggregations in a really interesting system. And overall things, if you check out the documentation, just the ease of use is something that I've really enjoyed. Getting your first schema set up with your database is really not too much trouble, and overall it's a really exciting thing that I'm really excited to be learning more about. So we'll start off with the question of why do you need vector search engines and what's inspired you to work on this project?
Yeah, thanks for having me. Yeah, you just mentioned a lot of the cases already that really work well. So essentially, the coolest thing about a vector search is that anything can be turned into a vector. So essentially, if you have your own models, completely doesn't matter if they're deep learning models or not. You can even use something as simple as like glove or fast text embeddings. Anything that can create a vector can be searched in a vector search engine. I think this is what makes it so cool and so versatile, because you can search through images, through text, through audio, through all these kinds of media. And because you don't have to do the model inference at search time, it's way faster. So for example, if we think about BERT, you could get a similarity score for 2 sentences. And then let's say you have a million sentences or 1,000, or doesn't really matter. If you, maybe I should do it the other way around, 1,000 or a million. If at query time, if you have to do the model inference between the query sentence and every sentence in your data set, this would cost you a lot of time and also resources. Like if it runs on GPUs, that's like very expensive. But in a vector database, essentially you do either you create those document embeddings, so to speak, either you create them up front or you create them at import time. And then at search time, all you have to do is the search similarity comparison, which is super fast. And we can get into sort of what makes it fast. But yeah, it's way faster than having to do a lot of model inference at search time.
Mm-hmm. And so what Etienne is getting into is the difference between, say, taking the dot product with your new inference and then everything in your database. So imagine that kind of dot product through everything in your database compared to where you build up these indexes. And so they're using this algorithm called Hierarchical Navigable Small World Graphs. And it's this really interesting way of where you have these centroids that kind of have like these local clusters that you can use to navigate through the nearest neighbors without having to do that dot product similarity with every single vector in your database. So what have been some of the key challenges with implementing that HNSW algorithm and then bringing that to the scale of these databases?
Yeah, so in general, when we want to bring it to scale, so you've mentioned right now already the sort of brute force example. So I'm just going to, I think there are basically 3 stages of scaling and of maturity on the journey to a vector search. The first one that you mentioned right now is just the brute force one. If there was no such algorithm, then you would just, let's say you have 10,000 or so objects, you can hold them in memory and you can just do the dot product or cosine similarity comparisons on there, nothing like that. But then still you have, from a user's perspective, you have a problem because you need to still store that stuff. So you're probably going to need a database. Like either the data set is static, that makes things a lot easier if your data set is static, but in real life it rarely is this static. So you would probably need a database anyway, just because you want to store those objects, like no vectors involved. But then if you add the vectors themselves, then you have to sort of mix and match, and I don't know, you have to retrieve them from memory. And this works well for tiny cases, but it really doesn't for larger cases. And as we started out with Weaviate, we basically did a proof of concept with a brute force search, actually. We just wanted to see, is there value in this thing in general before even worrying about the scale? So this was also the first stage that basically Weaviate was in. And it worked well with, 1,000 objects or maybe 10,000 objects, but there was no way that we could do this efficiently with 1,000,000 objects. And this was at the same time, basically, and this is sort of the second stage. And I think this is the one where a lot of people currently trying out with anything with vector embeddings where they're in, is we just pick something like a library for approximate nearest neighbor search. You've just mentioned one of them, the hierarchical navigable small world one, which from now on I'm just going to call HNSW because that's so much easier to say than the full name. But I wanted to say just once. So if you use one of those libraries, HNSW is a relatively new one. There are others before then. Essentially what they do is they make your search an approximate search. So you're sort of trading off the recall instead of 100% recall. Now, I don't know, it goes down only ever so slightly to 97 or 95% or something like that. But in exchange, you gain query speed, and with that query speed also comes higher throughput. Like if your CPU spends less time performing one search, that means that in, a second, you can serve more queries in general, which is very much sort of what you care about when moving to production. And this is, sort of the second stage, but there are a lot of limitations. Some of those are by the libraries itself. Some of those don't have, and we can get into the limitations in a second. But some of those are also based on the setup itself. Like if you have a library that's very far away or very far removed from running software in production. So basically that's where I see the third stage, where these vector search engines comes in, like Weaviate, for example. And that really means if you want to scale your data set out, because it grows too large to fit on a single machine, or because your throughput requirements, like even if you have a small data set, if you're serving a lot of customers and serving a lot of queries, you might need to somehow sort of scale that larger. And again, if your data set never changes, this might be really easy because, you can use one of those libraries, maybe build something once, put it in a Docker container, scale that up to, 3 or 5 or something instances, and you have sort of a scaled setup. But it's never that easy in real life because, data typically changes. So if you think of, for example, e-commerce, a web shop, products might go out of stock, new products might get added, descriptions might get changed, all these things. It's like it's always in motion. And that's really where some of the libraries can't handle this sort of incremental load at all. Some can, but even if they do, let's say you have this, cluster of 3 machines because you need it to be highly available, and then you need to change something that you deployed there. So all of a sudden what you're doing is no longer basically working on your models and making your models great, but now you're just sort of trying you've opened this whole can of worms of a distributed system. And that is definitely a challenge, but that is a challenge that we should tackle as the people building the database and not our users. So from our users' perspective, yes, they want the benefits of a distributed system. They want a scaled system, which can be highly available, which can scale dynamically and all these kind of things. But they don't want to worry about, sort of running a distributed system. So essentially, all these scaling aspects for our users should really just be configuration and not, sort of having to worry about, consistency or how nodes communicate in a cluster or these kind of things, which, are very interesting to us, but definitely shouldn't be to our users.
Mm-hmm. So you can just spin up something like an EC2 instance and then just back off. How much overhead would there be to setting up, say, a 8-node cloud distributed database for this?
Overhead with regards to time or resources?
Yeah, with regards to my setup. I could barely explain to you what Kubernetes is. Little experience. How much of a headache do you think it would be for me to get my own 8-node distributed database for, say, I want to take all the deep learning research papers and build up my Weaviate, and then I have this dynamic nature, as you say, where every time Archive sends me new papers, I go and add it to the database.
Oh yeah, that would be very easy. So to create a Kubernetes cluster, you don't need Kubernetes to run Weaviate, but it just makes life a lot easier. If you run it on one of the big 3 cloud providers, it's basically a one-click setup. And then Weaviate is deployed with a Helm chart, which is basically just a sort of easier way to manage Kubernetes manifests, because these are all these individual files for all the components. And then the Helm chart basically just ties it all together into one single thing where you have your configuration. And you just deploy that. It's one command to download it and one command to deploy it, and that's it. So I'm pretty sure we could right now, I don't know, get started and sort of minus the time that it takes the cloud provider to provision the infrastructure, we could probably deploy a distributed Weaviate cluster in less than 5 minutes.
Wow, that's to me, that's amazing that you can get just one click and then you got the whole thing set up. It's pretty crazy. So just to be, something that I would worry about, having gotten some AWS bills that, irritated me, what would be the cost? Like, do you have any sense of, or like, obviously it depends from how much you're using, but say a typical case where you just have 8 CPU nodes and I don't know, maybe like a recent blog post of the 60 million academic papers, how much do you think it would generally cost? Is that too much of a vague question to answer?
It's not too vague. Like I think it would be hard to answer it with concrete numbers, but it's definitely a calculation that we make every day for our customers, or that they make. So in general with HNSW, what we're using, the bottleneck is typically memory, because HNSW is graph based. We can also get into detail on that. And for this graph to work at full efficiency, the vector representations need to be held in memory. So basically the calculation is my vector. So let's say we have, I think you said something like 16 million, and then let's say they're, 200 dimensional, and typically they're like float 32, so 4 bytes. Then you basically you multiply that and you come up with a number, and you add a bit of overhead, and then that's the size that you need. So sort of 16 million is still a comfortable size. It can run pretty costly if it goes into the billions. That's also one of the limitations of HNSW that it has right now, that it sort of gets resource intensive on massive scale. But the typical sort of 16 million, this very much fits with the data set sizes that we typically see, which is between, let's say, a few thousand and a few million or so. We recently had a community user create a post about, I think, running, this was prior to Weaviate had the scaling feature, and they ran, I think, 60 million objects, or 60 million vectors. So an object always has a vector attached in Weaviate on a single machine. That was a pretty big machine, admittedly, but that still worked. So the cost should be very manageable with these sort of reasonably sized data sets.
So is the compute heavy part of this constructing the graph, and then as you're scaling up, adding new data to your database, when is it time to rebuild the graph? Is it a dynamic rebuild? How do you say, okay, we've added 2 million new instances, we need to rebuild this routing graph?
So the highest cost definitely is the building of the graph. So this is essentially on import, what you do in HNSW is you just do a search, and then basically the search tells you these are the closest neighbors, and then you just place it in the graph close to those neighbors. And then you run another algorithm to basically decide which of those neighbors are the ones that the new entry should be connected to. So the cost is definitely, the compute cost is definitely in creating the graph. However, as the graph grows, it never needs to be rebuilt. So this is the cool thing about HNSW. It's a completely sort of incremental process. And that's also one of the key reasons why we chose HNSW as the first. So by the way, the vector index type in Weaviate is completely pluggable, but right now HNSW is the first and only one so far. So in the future, we definitely want to add new ones. But the reason why we started with HNSW, as opposed to, let's say, for example, something like Google Scan in the ANN benchmark, so those benchmarks that do the query speeds over recall trade-offs, basically. Google Scan, for example, is better in those, but Google Scan has exactly that problem. You basically build it once, and then it's immutable. So with us sort of wanting to sort of produce an actual database and not maybe I don't know, a ANN serving engine or something like that. What we said is, well, what happens if you just build this thing and then, staying with the web shop example, a new product is added? Like, do you rebuild the entire thing just for one product? Or, I don't know, what do you do in this instance? And HNSW is completely dynamic in that sense, or that it can be built up in an incremental fashion. And as new products are sort of, let's say you've imported your data set, so to speak, of 2 million, and then you add another object. HNSW doesn't know that this one object was added later. It's the exact same process as you had to do for adding the original 2 million, which is why, in my opinion, it works really, really well for a database.
Very cool. And then all the ANN serving stuff is, say, like a HuggingFace endpoint. Is that like you don't... Is it connecting externally to the HuggingFace model inference API with something like the text-to-vec transformers?
This is something that could be done, and that is something that sort of our module system sort of works or would work with right now. Typically, you deploy those models yourself. But from Weaviate's perspective, it's the exact same decoupling, basically. So right now, we would run Weaviate is written in Go, which doesn't matter so much, but essentially you have this sort of one block of code that's running as a compiled binary in one container, so to speak. And then you have a second container, which might, for example, be written in Python, where we have the text-to-vec transformers module, for example, where right now you would run your own model in it. But sort of the request between Weaviate, so maybe just to explain why we even need that inference, one could be at import time, if you don't have your own vector embeddings and you want to sort of generate them at import time. But the second case is also if a search query comes in. So let's say a text-based query comes in, Weaviate needs a mechanism to turn that text-based query into this embedding. And and this right now, it basically sends an HTTP request to its model inference container, but it could just as well send that request to a third-party API, such as the HuggingFace inference API, which is something we've thought about, but haven't integrated that yet.
Super cool. So these are all the different components apart with the vector search engine, with having the vector representations and navigating through that. But then on the other hand, we have the symbolic query side, and there are things like the post-filtering and pre-filtering, how you can use these symbolic queries to first process and then do the vector search. So I was kind of curious about how that works, and just as maybe a little background for people listening, this neural networks struggle with having this neurosymbolic reasoning, where you try to have it act like an SQL database and do this filtering or this aggregation. And if you study things like relational algebra, where you have like the order of the join operations and these kind of things, it can really speed up your queries dramatically. So Weaviate has these two components where you store the data object, it has the symbolic properties as well as these vector representations. And I think that interplay is a huge part in also making this more searchable. So say you have these 60 million academic papers, but you want to filter them on, say it's deep learning papers, and you want to say, I actually only want to search through publications in ICLR, ICML, NeurIPS. You would use that symbolic query as the pre-filtering, right, with the pre-filtering, so it would dramatically reduce the vector space it needs to search through. So I was curious about how this pre-filtering, post-filtering thing plays together with the vector search and then the symbolic filtering.
Yeah. So funny thing is, as I mentioned before, that we started out with a very simple proof of concept sort of before we had any kind of ANN model. And for this, we actually just plugged in an existing sort of traditional text-based search engine. And that is where those filters already existed. So we said, okay, when we build our own database, we like that feature so much, and we actually saw it in our early use cases. We saw people actually set those filters, and we said, like, from the beginning, this is something that we want to have as well. And then we sort of saw these different libraries, and I already mentioned some of the limitations of some of them. But then we realized, okay, this actually doesn't exist in any of those libraries. All they can do is do the similarity comparison. And what you could do, if you know upfront which filters the users are going to set, and well, you never know, but if for whatever reason you knew, you could say, okay, I'm just going to build one graph for this property, one graph for this property. But then if they're not set, for example, then you have to search 3 graphs and these kind of things. So what we said is, well, it looks like we want to use this HNSW algorithm, but we can't really we can't use the existing library for it, but maybe we can modify it. And by modify it, I don't mean modify the library, but basically we just recreated HNSW according to the paper as it is in the library, but we added a filter step. And for this filter step, you just mentioned pre-filtering and post-filtering. And just to explain, I'm not sure if everyone is familiar with those two terms, but post-filtering would be the sort of the very simple thing where you just do your vector search, and then after you've completed your vector search, let's say you've returned 100 objects, you then check which of those results matches your filter. And this can work well if your filter is not very restrictive. So if on average 90% of your objects match that specific publication that you mentioned, for example, if that is the case, then let's say you ask for 100 nearest neighbors, then on average you would still have 90 left on that list if they were evenly distributed, which of course they're not, but just in theory. But now let's say your filter is really restrictive and you're restricting it to just 1% of your data set. What are the odds that this search that was completely unrestricted actually contains any of those things that you filtered for? So as the filter gets more restrictive, post-filtering basically breaks. So here's where we use pre-filtering. Some of our competitors also call this, I think, single-stage filtering, but essentially it's the same process. We just call it pre-filtering. Where in pre-filtering, you use sort of the traditional means for searches, which is typically an inverted list. So basically, if in a book or something, you have in the end you have this lookup list, and it just tells you go to that page. And that is the same process in an inverted list, which essentially tells you, okay, if you search for this search term, you need to use this document ID. And we use this mechanism as well, but basically instead of returning just the list, because we still want to do a vector search, we just use the inverted index to build up this sort of allow list of allowed IDs. And this happens to fit really well with the HNSW algorithm, because the HNSW algorithm basically at search time, it evaluates candidates and it evaluates the candidates' connections. And then in the end, the best ones are added to the result set. And at some point, if the result set is full and the results don't improve anymore, then basically it says, okay, we're done. And that makes it an approximate search. Otherwise, if it just continued forever, it would be a sort of actual, flat search. And in this process, we said, okay, this is super cool for us because we can still use those candidates to jump through the graph, because that's what makes the search efficient, by jumping through the graph. But basically, if the filter isn't applied, and by that time, we don't do the filter anymore, but the filter at that time is just checking of, is it on that list that we created beforehand? And if it is, then we add it to the result set. If it's not, we don't add it to the result set. And this works really, really well. We actually have, because we got a few questions about this, but sort of, how does that work with the filter? Like if the filter gets more restrictive, how does it work? And it works really, really well up to, I think, typically filters that are 95% restrictive or so. So if you have a filter that matches a large portion of your data, then it's basically just, so if that was 100% on the list, that would basically just be the same as an unfiltered vector search. And as it grows lower and lower, the graph, basically you have to jump through more connections in the graph until you find a match. And up to like something like down to 5% or so, this works really well. And then the cool thing is the point at which the graph isn't efficient anymore, your data is so restricted that you can just do a brute force search. So at some point, there's just this cutoff where you have so few data points that you can just do a flat search on it, and then it's efficient again. So basically, you have this nice curve of very efficient search with pre-filtered search with Weaviate.
Yeah, well, it's so interesting to me, the combination of the symbolic and how you can filter down the search space and then do the vector nearest neighbor. And so tying this back, this has been one of the areas of research that I've been the most excited about, is following along with things like retrieval augmented generation and say the Realm model from Google, or again, retrieval augmented generation is from Facebook AI, but things like dense passage retrieval. And what they're looking to do is we're looking to augment language models or generative language models with additional context. So usually what we're doing is we're taking our query, we have like a question answering system, and we're taking our question and we're trying to go find, say, Wikipedia documents that can help us give more context to this model for answering it. So what Weaviate is building is they have this symbolic filter so that instead of just doing this, something like a dot product with all the Wikipedia documents, you can use symbolic queries to filter through the document index. And we have things like Facebook AI recently published a paper called Internet Augmented Generation, where they're learning to query the Bing search engine API in order to get the results for this context. So you could imagine a similar pipeline where it can use Weaviate's symbolic query system in order to speed up its access, in order to access its context. And I see this Weaviate component being a huge part of the future of language models, really, because if you look at things like there's a recent paper on studying compositional generalization in these language models, and when you have context, it makes an enormous difference with how well these models can do compositional generalization, which is generally kind of like the holy grail in my understanding of these language models. So I see this component of having the symbolic search just being a huge part of building the next generation. And then another thing that I just love about Weaviate is the modularity of it, how easily it will plug and play into these other components, like, again, the internet augmented generation thing where you just have this API. You similarly just have this Weaviate API layer on top of your database, and now your language model can access it and become more intelligent with using this querying. So overall, I just think it's so interesting seeing this neurosymbolic system, and I definitely think that having the filtering, having kind of like this SQL part of it is going to be a really important part in these vector search engines. So then one other thing I wanted to talk about with respect to modularity and Weaviate is this trend we're seeing in the availability and accessibility of data sets in deep learning. So I'm sure most people listening are aware of HuggingFace datasets. They are indexing, I think, this is probably going to be an incorrect number, but I think it's something like 1,500 datasets, where you can just go into your Python library, go pip install datasets, load dataset, and then you got 1,500 datasets that are ready to go. And that's different. That's definitely a new trend that I'm seeing in deep learning. And also, Kaggle has been indexing datasets forever, and now PapersWithCode also has papers with datasets where they're also collecting and organizing these datasets. So on top of that, we have Streamlit and things like that let you quickly have this front-end web interface where you can quickly look through the databases. And what Weaviate to me, it will be another layer like Streamlit, where you can not only just look through the databases, like see like a pandas data frame where you do df.head and see the first 10 rows, you'll be able to do these kind of symbolic queries, vector searches, right in, say, a web UI. So I did want to ask quickly about how easily that Python client accesses the databases. It's really easy to just kind of plug this into different applications, and this modularity of it, like how easy is it to just call the Python API with Weaviate?
Yeah, that should be very simple. I think in general, you have a setup call where you basically just need to connect it. So Weaviate being a database, it needs to run somewhere. So sometimes in the Python world, it's very typical that you use just these sort of frameworks or libraries that are often C code that basically are spun up directly from wherever the Python code runs. That's not the case with Weaviate. It's it's a database that runs as its own sort of separate instance. So you need to connect to it, and that is just one step. Basically, you just put in the address. If you're running on your local machine, it would be something like localhost 8080. If it's running on some sort of a server, you put in that. And that's the first command. And then once you have the client, I think that the second one would just be to do the search. And if you're using this together with one of the modules, so let's say you have the text-to-vec transformers module, and you're using any kind of model for your vector embeddings. If that was used during import, then you can also use it, as I said before, to generate the embeddings on queries. So you literally just have one command to put in your natural language question and send that to the API, and it would return your results from either a single machine or a cluster or all these things that I mentioned before, of sort of abstracting away the hassle of running the software in production.
Mm-hmm. And okay, so stop me if what I'm saying right now is totally incorrect. I'm not sure. Can you put this entirely in the web browser? I've seen where you can create the Python client locally and you can load the database, you could like create the schema and kind of spin it up. Could you do this all locally in the browser without even having to send an API call to a cloud database?
In theory, yes. It's not something that we've ever done, simply for the reason because no one's asked for it. But it does actually work with the WASM, I think, the WebAssembly thing, where you can basically run arbitrary code in your browser. Weaviate being written in Go, you can basically just set your compile target. So typically we compile for I don't know, Linux on AMD 64 architecture, or these kind of, if it were running on a Mac for development, then for Mac. One of the compile targets that we could specify would be the WebAssembly one, and then you could actually run that entirely in your browser. Yes.
Yeah, that's, to me, it seems like that integration with like the Streamlit web application, search through a database, thousands of data sets indexed. I see this being just a huge part of deep learning research and just facilitating the access to these data sets. So I also want to get more into these modules. So in addition to, we've talked about text-to-vec, mentioned that a few times. That's the module where you've loaded some model and you're not passing in the vectors to the database. You want to on the fly compute the vector encodings. But there's also things like question answering, natural language inference, and like image to vec and other kinds of data domains to vector. Can you explain like the question answering module and how that works and how that's different from just text to vec?
Yeah, sure. Just maybe in general on the module system, the idea really is that there are certain things in Weaviate that are basically fixed from a user's perspective. That is basically the persistence layer, how we do things, and there are things that are sort of wide open, where Weaviate says, say, okay, you can hook in, I don't know, prior to or sort of after a object is sent for indexing, but prior to it being stored in the database, which is typically where the text-to-vec would come in. So, and Weaviate is entirely agnostic of what the module does with it. So in the case of text-to-vec, we really just give the module the entire object, and the module then, based on its configuration, says, okay, I want to use, I don't know, only this property or some of those properties or these kind of things. Or if it's an image, then this field contains the base 64 encoded image, etc. And basically the contract with Weaviate is that when it returns it, it needs to provide a vector for it. And so Weaviate in this part is completely agnostic, and all the sort of business logic that goes into the vectorization process lies with the module. So this is what we call a vectorization module, because it does the text to vec or the media to vec. But in general, the module API isn't limited to vectorization. So you just mentioned the question answering module. And that it's actually a super cool example for the scaling aspects of a vector search, because essentially what it does, it's not very different from an off-the-shelf sort of question answer extraction model. I don't know, that's like a downstream trained task for a BERT model, for example, where you put in your question and then you put in your paragraph that contains the answer, which I think with the typical BERT limitations has to be limited to something like 512 tokens. So now Weaviate comes in, because you don't want to get your answer from 512 tokens. You don't even want to get your answer just from a single document, because if you already know the document that you want to get the answer from, that's easy, but you might have millions of objects. And this is where the question answering in the question answering module in Weaviate is basically a two-step process, where first we take the entire question and we just vectorize it in the same process as we do with the text-to-vec process, just to find the document. And then once we have the document, then we basically run the question answer extraction process over it. And there also, to overcome the limitation of 512 tokens, we basically have a sliding window over the entire document, and then we just compare which of those possible answers has the highest certainty, and serve that to the user.
Mm-hmm. And then the other thing that I think is just really, really cool is text to image, and this whole thing. I think also combining the text to image with the symbolic filtering also is so exciting. We see things like a common thing that we're seeing is people are using, say, the vector quantized GAN to generate a ton of images, and then you use the OpenAI clip model where you have the contrastive learning training of the text embedding, image embedding similarity to find these funny images where you have a prompt like a banana doing stand-up comedy, and you do the embedding matching to get these kind of things. And So what's the state of the text to image matching in Weaviate, and kind of what are your visions on how building that out will look?
Yeah. So we haven't actually run with a model yet that has a sort of combined vector space for text and images. But because of the decoupling in the module system, this would be super trivial to add if such a model exists. So this is basically the point where Weaviate says, like, I don't care where the vector comes from. If a model can do it, I work with it. And maybe we have to add a new module for it for just because of the API changes or something. Let's say, if you're searching by text but you're expecting images, no, actually that would even already work with the existing one. So really, you just have to plug in the model that can do it, and as long as the vector embeddings are compatible with one another, you can serve it. And sort of from the perspective of Weaviate, you really just serve objects, and what media type they have or where they come from, it really doesn't care.
And we've even seen papers like pre-trained transformers or universal computation engines that maybe a clip-like model, maybe you don't need a particular vector joint embedding space for every different multimodal pairing, like audio, vision, time series, audio, or whatever. Maybe you don't need to enumerate the entire space of possible pairings. Maybe it is possible that you can just have like a clip that would work for any kind of multimodal inference, I guess, like a zero-shot pairing, or maybe not zero-shot, but something like that. Anyways, overall, just the modularity of it, the ability to just combine these vector spaces and these new applications, like some things we quickly mentioned, like the text to image that we just got out of, and things like using the retrieval generation, the question answering. All of it I see is just having a massive impact, and overall, just this vector search engine is a really exciting thing that I see as being a new kind of generation of search. Maybe that's too grandiose, but I definitely see that.
I think it is. Well, I'm biased, but but I definitely agree with you on that one.
Yeah, it seems to me like a huge paradigm shift in search with these representations and definitely all that. So maybe sort of as like a last question, just what inspired you to, like, if you could take me through your journey where you were working on something else and how you decided to work on this. How was that inspiration for you?
Yeah, I think there's really, so when I joined the team, we weren't really building a vector search engine yet, and that is because at that time no one was building a vector search engine, or if they were, they wouldn't use the term vector search engine because the whole concept didn't exist. So at the time, Weaviate, and this is something that we have in it up until this day, is the sort of graph-like system where you can make graph connections in Weaviate. At that time, when I joined the team, basically Weaviate was sort of going in the direction of a graph database, or maybe as a layer on top of a graph database that would then also try to make use of embeddings. And at the first goal that we had was just to create embeddings for the schema. Like, we didn't even think of the individual objects yet, but just for the schema. And at some point then we were playing around and we were just thinking, hey, wouldn't it be really cool if you could create that just for not just for the schema, but for anything? If you just throw anything at it and create an entirely new generation of database or search engine, basically. And we did that, and we tried that, and it worked surprisingly well. And this time we hadn't heard yet of BERT models or of transformer models in general. I think they already existed, but I don't think anyone tried to create document embeddings yet from it. It was basically just the typical downstream tasks that you have from BERT models. So all we did was just use glove embeddings, and to this day you can still use that with one of the Weaviate modules, which is called the contextionary module, which uses sort of old school, so to speak, text such as glove and fast text, but also doesn't require GPUs and works surprisingly well for a lot of use cases. So it turns out this is actually, if you move away from cutting edge research and more into sort of some of the cases that our users actually want, it works really well for them. So it's definitely a very popular module. Yeah, we just tried this out, basically just taking mean embeddings from different words that were contained in these glove outputs, and just mix them together. And there was no research background on it or something. It was basically just trial and error, and we're like, oh wow, this works. There really is something there. We really need to do that. And then we sort of, at first it was like, yeah, but I mean, what are we going to do? Are we going to build a database? I mean, come on, that's like, you don't just start building a database from scratch because, well, just, I mean, I've kind of liked the idea, and I thought like that would be an interesting project to learn something myself. But we slowly transitioned into that, and sort of proof of concept after proof of concept, we thought like, wow, this is there really is something there, and we need to turn this into an actual product. And then my background in software engineering and in working with cloud and DevOps kind of topics, my focus was always like, okay, whatever we do, this needs to be production quality. Like there are people who are doing these experimental setups already that are great for research, but that's not necessarily our focus. We want the people that have completed the research and that say like, okay, I want to implement this. I want my company to make money with this, and for this software needs to run in production. And that was then really the focus and the motivation to say like, okay, we're not going for, I don't know, an API wrapper around a Python library, but we're really trying to build up production quality software from scratch.
Super cool. Awesome. So thank you so much for being a guest on the Henry AI Labs show. I'm really excited to do more and more videos about Weaviate. As you know, I'm personally building I got my schema set up and I have my databases in there, so my datasets in there, so I'm starting to use it for my research, and just such a cool thing, and I'm really glad to be working with you all like this, and really cool. So the best way for anyone listening to have their questions answered, would it be the Slack chat? Is there like a email where you respond to questions, or how could people get in touch with you?
So the easiest to discover might just be the GitHub repository, which has the links to everything. You can use GitHub for issues itself with the software. You can use the Slack channel for questions. You can use the documentation just to get started and to see how to use it. Yes, I think the if you put the link to the GitHub the GitHub repo and the documentation in the description, and I think that's a great starting point for everyone.
Awesome, cool. Yeah, and just again, anyone starting out, the documentation is great, super organized, easy to read, and getting your schema set up is, pretty easy. They walk you through an example where you're storing news articles, and you have the publication, the author, and I forgot the third thing, but there are three classes, the class property.
Author, article, and publication, I think.
Okay, yeah, got it. Yeah, but super easy to get started. Thanks again, and stay tuned for more content. And also check out Weaviate Semi-Technologies. They have a YouTube channel as well where they have meetup events, walking through new updates, and all sorts of content. Also more content coming on Henry AI Labs. So thanks again, Etienne. And
thanks for having me. Bye.